Now that we've covered covalent bondings in some substance, let's look at bonding theories. Be able to define molecular orbital. This is when you have two atoms next to each other and their orbitals kind of overlap to form this molecular orbital. Bonding orbital is the specific molecular orbital occupied by two electrons, and that can be in the form of a sigma bond, which is going to be the two s orbitals, which are going to be around each other, or a pi bond, which is when two p orbitals are going to be part of a molecular orbital. We are not covering hybrid orbitals in this class. Be able to define tetrahedral angle, which is one of the angles we're going to look at with different molecular shapes, and the VSEPR theory, hard to say it actually, VSEPR theory, and we'll cover that a little bit later. Be able to predict whether a sigma bond or a pi bond or both will be present if given a covalent bond, a single, double, or triple bond. Use the VSEPR theory to predict molecular shapes, and I'll point out that we do cover HSPS 1-3 and 4 when we're looking at the strength of electrical forces between particles and the total bond energy, including bond shapes. So molecules have electron orbitals. Now think about it this way. You have two atoms and they're next to each other. So what do the electrons look like? Are the electrons just orbiting each atom individually, like you'd have two billiard balls basically? Or is it one gigantic sphere? Or is it kind of shaped almost like a watermelon? I mean, really starting to think about where the electrons are in a molecule. So this is H2. Well, let's look at H2. What it would look like is you'd have each nucleus is attracted to wherever the density of electrons is highest, which is technically between the atoms. But the nuclei are repelled by each other because two positive charges don't go next to each other easily. So what the molecule will end up looking like is like an oval sphere. So a little less like two billiard balls and much more like a watermelon, perhaps a little divot in the middle. And that's what we call a sigma bond. So you have the two s orbitals, each of which has a single electron in it, and they overlap somewhat to form a sigma bond. So that's where you have that symmetrical around the axis kind of distribution of electrons. That's a molecular orbital right there, or specifically a bonding orbital called a sigma bond. Now what about having the p orbitals? Now you can actually have two separate electrons in separate p orbitals also forming a sigma bond. So just remember that too. Pi bonds are the next type of bond, and those are going to be a little weaker than sigma bonds. Pi bonds can only exist when there is already a sigma bond. So sigma bonds form first, then pi bonds form. And if we're talking about sharing multiple electrons, so you share two electrons in a sigma, and then you share two more in a pi, well, that's 4 electrons total, and that would be a double bond. What if you share two more, like a triple bond? Well, you're just going to form another pi bonding orbital. How does this influence how molecules are shaped? And this is actually kind of interesting because we don't often think about the shape of a molecule until we get down to the nitty and the gritty and think about, well, if the molecular orbitals are shaped like thus, how are the atoms shaped in three-dimensional space? And something like carbon dioxide is going to be linear. You have the two double bonds on either side of the carbon forming a linear shape. Why? Well, VSEPR is why. The valence shell electron pair repulsion. Think of it this way. You want to get those bonds as far away from each other in space as possible. So that leads to this linear, trigonal, planar, tetrahedral. That's when you have 4 bonds, you get a tetrahedral molecule where you have these 109.5 degree angles between these, and that's in 3-dimensional space, remember, so it looks kind of like a pyramid, really, a tetrahedron to be precise. Now you look at this trigonal, bipyramidal, and octahedral shape, and you're like, wait, there's 5 bonds and 6 bonds? Well, remember I said sulfur and phosphorus can form more bonds, and we're not really going to get into that too much. What I do want to look at is when you have unshared pairs. When you have unshared pairs, this is actually going to also bend the molecule. And that's going to make a bent molecule or a trigonal pyramid molecule instead of a trigonal planar or tetrahedral. Here's why. You have the space occupied by those negative charges in an unshared pair is going to occupy more space than your actual molecular orbitals because they are more negative. There's a larger negative charge. So think of it this way. You've got 4 balloons around a carbon. And that's going to be your tetrahedral angle. But you end up having this pyramidal angle when you have nitrogen bonded with 3 hydrogens and having an unshared pair of electrons, like having these balloons next to each other. This bent geometry moves the pairs away from each other, so these bonds are moved, and you have an 170-degree angle instead of an 109.47-degree angle. So it just makes a slightly different shape when you have these unshared pairs. Okay, seems kind of abstract. It's not. This actually matters for the shape of water. You have 2 unshared electron pairs. So go back up here. You have 2 unshared electron pairs, so you end up with this bent molecule right here, 2 lone pairs. Why does that matter? Well, when you look at the shape of water, you're going to see that it forms, you actually have more of a negative charge on one side, a higher electron density on one side, and a more positive charge on the other side, and that's going to make water's polar. It also is the reason for shapes like snowflakes, and that's going to matter a lot when you actually look at the chemistry of water more specifically. We'll get back to that later, or you'll cover it in biology.